Welcome to part 2 of the exercises. The terrain gets stranger now. We build a world where every distance equals 1, and watch open, closed, and compact change meaning. We audit 5 candidate distance functions and unmask 3 impostors. We prove a set compact with our bare hands, straight from the definition. We break the nested compact sets theorem in 2 different ways. Watch Heine Borel fail inside the rational numbers, and finish with 2 showpieces. The set of 4s and 7s, and a perfect set containing no rational number at all. Let X be any infinite set, and define the strangest possible distance. The distance between 2 points is 1 if they differ, and 0 if they coincide. Every pair of distinct points sits at distance exactly 1, like the corners of a perfectly symmetric web. We claim this is a genuine metric, and then we will explore the bizarre world it creates. The axioms, checked live. Positivity. Distinct points have distance 1, which is positive, and each point has distance 0 to itself. Symmetry. The rule only consults whether the 2 points are equal, and equality does not care about order. The triangle inequality is the only one with content. Take 3 points. If P equals Q, the left side is 0, and there is nothing to prove. If P differs from Q, then the midpoint R cannot equal both of them. Watch. Whichever edge R fails to collapse contributes a full 1 to the right side. So the right side is at least 1, which is the left side. All 3 axioms hold. A genuine metric. Which subsets of this world are open? Watch the ball of radius 1/2 around a point P. Every other point sits at distance 1, which is more than 1/2, so nothing else fits inside. The ball is just the single point, P. A neighborhood that equals the singleton means the singleton is open, and the point P was arbitrary. Every 1-point set is open. Now take any subset A whatsoever. Say these 4 points, glowing sage. A is the union of its singletons, each of which is open, and a union of open sets is open. So every subset of X is open. But then look at the complement of A. It is a subset too, hence open, and a set whose complement is open is closed. Every subset of this world is simultaneously open and closed. The topology is as fine as it can possibly be. Finally, which sets are compact? Take an infinite set K and cover it by the singleton balls. One tiny ball pops over every point, all the way down the endless row. This is an open cover, but each cover set contains exactly 1 point of K, so any finite subcollection covers only finitely many points, and infinitely many remain exposed. No finite subcover exists, crossed out. Infinite sets are never compact here. Finite sets always are, in any metric space. Pick 1 cover set per point, and you already hold a finite subcover. So in the discrete world, compact means exactly finite. Now an audit. Here are 5 candidate distance functions on the real line. The squared difference, the square root of the difference of squares, the lopsided x minus 2y, and the bounded ratio. Exactly 2 of them are genuine metrics. We unmask the 3 impostors first, each with a concrete counterexample, drawn live. First impostor, the squared difference. Put 3 points on the line, 0, 1, and 2. The direct distance from 0 to 2 is 2 squared, which is 4, the long rose bar. But the detour through 1 costs 1 squared plus 1 squared, which is 2, the 2 short bars. 4 is greater than 2. In a metric, the direct route can never beat the detour by being longer, so the triangle inequality fails. Cross out the first candidate. Second impostor, the difference of squares. Take the points 1 and minus 1. Their squares are equal, so the candidate distance between them is the absolute value of 1 minus 1. Which is 0. 2 genuinely different points, connected by a distance of 0. A metric must assign positive distance to distinct points, so positivity fails. Cross out the third candidate. Third impostor, x minus 2y. Tested on a single point. The distance from 1 to itself is the absolute value of 1 minus 2, which is 1, not 0. A point at positive distance from itself, the little loop in the picture. It even fails symmetry. From 0 to 1, it gives 2. From 1 to 0, it gives 1. Doubly disqualified. Cross out the fourth candidate. 2 candidates remain, and both will survive. Fourth candidate, the square root of the absolute difference. Positivity and symmetry are inherited from the ordinary distance, since the square root of a positive number is positive, and of 0 is 0. The whole battle is the triangle inequality, and it rests on one inequality. The square root of a sum is at most the sum of the square roots. Why? Square the right-hand side. It equals a plus b plus an extra block of 2 square root of a b. Compare the bars. The squared right side carries everything the left side has, plus a bonus block. Larger square root. Now chain it. The ordinary triangle inequality puts x to z below the sum of the two legs. Monotonicity of the square root preserves the comparison, and the key inequality splits the root of the sum. 3 links, and the triangle inequality holds. The square root distance is a genuine metric. Last candidate, the bounded ratio, the ordinary distance divided by 1 plus itself. Positivity and symmetry are again inherited. For the triangle inequality, study the function f of t equals t over 1 plus t. There is its graph, climbing steadily but never reaching the dashed ceiling at height 1. It is increasing. So, start from the ordinary triangle inequality. The distance from x to z is at most a plus b, the two legs. Feed both sides into the increasing function f. Then, split the fraction f of a plus b into 2 pieces over the common denominator, and enlarge each piece by shrinking its denominator. A over 1 plus b is at most a over 1 plus a, and likewise for the b term. Watch each link flash. The result is exactly the sum of the 2 candidate distances. The bounded ratio is a genuine metric, and as a bonus, it shows that any metric can be tamed to take values below 1. Now a rite of passage. Prove a set compact directly from the definition, with no Heine-Borel allowed. The set, 0 together with all the reciprocals 1 over n. Compact means every open cover, no matter how malicious, admits a finite subcover. So let an arbitrary open cover be handed to us, and watch us extract a finite subcover by hand. Step 1. The point 0 belongs to the set, so some cover set, call it G0, contains 0. G0 is open, so it contains a whole ball of some radius r around 0, the lavender ball. And here is the decisive moment. By the Archimedean property, every reciprocal 1 over n with n beyond 1 over r lies inside that ball. Watch the entire infinite tail light up inside G0 in a single stroke. One cover set has swallowed all but finitely many points of the set. Step 2. Who is left outside? Only the finitely many large reciprocals, at most 1 over r of them. Here, 1, 1/2, 1/3. Each of these points is in the set, so each lies in some set of the cover. Pop a set over each straggler. 1, 2, 3. And we are done. G0 plus 1 set per straggler. 1 plus m sets in total, a finite subcollection that covers everything. The cover was arbitrary, so every open cover has a finite subcover. The set is compact, proved with bare hands. Next task. Construct a compact set of real numbers, whose limit points form a countable set. The idea: clusters of clusters. At every reciprocal 1 over n, hang a small staircase of points marching down toward it from the right, kept inside the gap up to the previous reciprocal, so the staircases never mix. Watch them appear. A staircase falling into 1, a smaller one falling into 1/2, into 1/3, and so on. Then include the anchors 1 over n themselves, and the point 0. Now read off the limit points, marked with rose rings as they are certified. Each staircase converges to its anchor, so every 1 over n is a limit point. The anchors themselves march down to 0, so 0 is a limit point. And nothing else qualifies. Away from the rings, any point has only finitely many neighbors of the set nearby, and we shrink a ball past them exactly as in part 1. So the derived set is 0 together with the reciprocals, a countable set, as requested. Finally, compactness. The derived set is contained in the set itself, so the set is closed, and it lives inside the unit interval, so it is bounded. Closed and bounded in the real line. By Heine-Borel, compact. Here is the canonical bad cover. Cover the open segment from 0 to 1 by the sets Gn, the open segments from 1 over n to 1. Watch them stack. G2 reaches back to 1/2, G3 to 1/3, G5 further, G12 further still. Every point x of the segment is positive, so by Archimedes, some 1 over n drops below it, and x is covered. This really is an open cover of the whole segment. Now try to thin the cover to finitely many sets. A finite subcollection has a largest index, call it n, and since the sets are nested, its union is exactly the segment from 1 over n to 1. Everything to the left of 1 over n is abandoned. There it is, the rose strip near 0, flashing uncovered, crossed out. The point 1 over 2n, for instance, belongs to the segment but to none of the chosen sets. No finite subcover exists. The segment from 0 to 1 is not compact, and this cover is the witness. We proved that nested, non-empty compact sets always share a common point. Is compact really needed, or would closed do, or bounded? Both weakenings fail, and here are the counterexamples. First, closed alone. Take the rays from n to infinity. Each is closed, each is non-empty, and they are nested, each inside the previous. But their intersection is empty. Take any candidate point x, here at 2.5. The moment n climbs past x, the ray from n onward expels it, crossed out. No real number survives every ray, so the intersection is empty. Closed is not enough. The sets escape to infinity, which boundedness would have prevented. Second, bounded alone. Take the open cells from 0 to 1 over n. All of them live inside the unit interval, so they are bounded, non-empty, and nested, each inside the previous. But any candidate point epsilon is positive, and by Archimedes, some 1 over n drops below epsilon, expelling it, crossed out again. And 0 itself is in none of them. The cells are open on the left, so the intersection is empty. Bounded is not enough either. This time the sets failed to be closed, and the candidate limit leaked out through the open end. Compactness, closed plus bounded, is exactly the combination that plugs both escape routes. Now we change universe. Forget the real line. Our entire world is the rational numbers, with the usual distance. Inside it, let E be the set of rationals, whose square lies strictly between 2 and 3. On the positive side, that is the rational dust, strictly between root 2 and root 3. And there is a mirror image on the negative side. But notice the two hollow fence posts. Root 2 and root 3 are irrational. In our universe, those posts do not exist. They are holes in the world, and everything strange about this example flows from that. 3 properties, drawn live. First, E is bounded. Every element has absolute value below root 3, hence below 2. Second, E is closed in the rational universe. Take a rational P outside E, say here, just below root 2. Its distance to the missing post is a positive protective gap. Draw a ball smaller than that gap, and the ball misses E entirely, so P is not a limit point of E. The only locations where limit points of E would accumulate from outside are the posts themselves, and they are not rational. In this universe, they simply do not exist. So E contains every limit point it has, and E is closed. Third, the surprise. E is also open. E is the rationals intersected with an open set of the real line. So every point of E keeps a whole rational ball inside E. Watch the sage ball fit. Closed, open, and bounded all at once. And yet E is not compact, and we prove it with a malicious cover, exactly in the spirit of the bad cover of the open segment. Let Gn be the rationals strictly between root 2 plus 1 over n, and root 3, with mirror sets on the negative branch. Watch the bars creep toward the missing post. G8, G20, G60, each starting a little closer to root 2. Every point of E is a rational strictly greater than root 2, so some 1 over n fits underneath it. The bars do cover all of E, and each bar is open in the rational universe. Now thin the cover to finitely many sets. There is a largest index n, and the chosen bars only reach down to root 2 plus 1 over n, but the rationals are dense. In the gap between root 2 and root 2 plus 1 over n, rational points of E exist, and there one is, flashing rows, abandoned by every chosen bar. Crossed out, no finite subcover. So E is closed, bounded, and not compact. The moral is the whole point of this exercise. Closed plus bounded implies compact is a theorem about Euclidean space, not about metric spaces in general. Move to a universe with holes, like the rationals, and Heine Borel quietly dies. And as a final twist, remember E is also open, a set that is simultaneously open, closed, and bounded, yet not compact. Now the star of part 2. Let E be the set of all numbers in the unit interval whose decimal expansion uses only the digits 4 and 7. Every digit, forever, is a 4 or a 7. Watch what the digit choices do geometrically. The first digit being 4 or 7 confines the number to 2 closed cells. Inside each cell, the second digit again chooses between 2 children. Then again and again. 2 children per cell, every level, forever. The set E is exactly the points that survive every round, the intersection of the closed stages CK. If that pattern looks familiar, it should. It is the Cantor construction, with deletion driven by forbidden digits. Everything we loved about the Cantor set is about to reappear. First question, is E countable? Take any infinite sequence of zeros and ones and watch it transform. Every 0 becomes a 4, every 1 becomes a 7. The result is a legitimate element of the set. Distinct sequences disagree at some position, so they produce numbers whose expansions disagree at that digit. Distinct elements. That is, an injection from the set of all 0-1 sequences into E. And we proved in the countability video that the set of all 0-1 sequences is uncountable. A set receiving an injection from an uncountable set is uncountable. So the answer is no. E is uncountable, despite being carved by such a rigid digit rule. Second question, is E dense in the unit interval? Look where E actually lives. The sage cells sit near 0.4 and 0.7. Now look at the rows segment from 0.5 to 0.6. Any number strictly inside it has first digit 5, and 5 is forbidden, so the segment contains no point of E whatsoever, crossed out. Dense would mean every segment meets E, and here is a segment that does not. So E is not dense. Uncountably many points, and still entire neighborhoods are left completely empty. The same paradox the Cantor set taught us. Third question, is E compact? The cell picture makes it one breath. Each stage CK is a finite union of closed intervals, hence closed. Watch the stages stack. E is the intersection of all the stages, and an intersection of closed sets is closed. E also lives inside the unit interval, so it is bounded. Closed and bounded on the real line. By Heine Borel, E is compact. And the finale. E is perfect. Take any element x, its digit stream written out, and any challenge radius h. Choose a position n far enough out that 3 times 10 to the minus n plus 1 is below h. Now flip the digit in position n plus 1. A 4 becomes a 7. Watch it swap. The new number y still uses only 4s and 7s, so y belongs to E, and y differs from x. All digits before and after the flip agree. So the distance between x and y is exactly 3 in that decimal place, smaller than h. Every neighborhood of x, however small, contains another element of E. X is a limit point, stamped with the rose ring. The point x was arbitrary, E is closed, and E has no isolated points. E is perfect. Uncountable, nowhere dense, compact, perfect. The set of 4s and 7s is a true cousin of the Cantor set, built from digits instead of deleted thirds. Before the final construction, one lemma about rational numbers, proved with a picture. Claim, every rational P over Q has a decimal expansion that eventually repeats or terminates. Run the long division of P by Q. At every step, the remainder is one of only Q possible values, from 0 to Q minus 1. Here is 1/7. The remainders march 1, 3, 2, 6, 4, 5, around the circle. And by the pigeonhole principle, within Q plus 1 steps, some remainder must appear a second time. Watch the cycle close back to 1. From equal remainders, long division produces equal next digits, and equal next remainders, forever. The digit string locks into a repeating block, 1, 4, 2, 8, 5, 7 for 1/7. And if the remainder 0 ever appears, the expansion simply terminates. Either way, eventually periodic. Hold on to the contrapositive. A number whose digits never become periodic cannot be rational. And now the finale of part 2. Goal. A non-empty perfect set on the real line containing no rational number whatsoever. The 4s and 7s set is perfect, but it does contain rationals, for instance the repeating number 0.4747. The fix is a translation. Let A be the number whose expansion has beacons of 1, separated by ever longer blocks of zeros, 101, 001, 0001, and so on, forever. Define F to be a plus E. Every element of the 4s and 7s set, shifted by A. Add it to an element X of E, column by column, and watch the digits. Where A has a 0, the digit of the sum is the digit of X, a 4 or a 7. Where A has a beacon of 1, the digit becomes a 5 or an 8, glowing rows. And crucially, 4 plus 1 and 7 plus 1 stay below 9, so no column ever carries. The digit pattern of the sum is completely transparent. The sum is a stream of 4s and 7s, interrupted by 5s and 8s exactly at the beacon positions of A. Now the two punchlines. First, every element of F is irrational. The 5s and 8s occur forever, since it has infinitely many beacons, and the gaps between consecutive beacons grow without bound. But if the digit string were eventually periodic with some period, then in the periodic tail, the special digits would recur with bounded gaps. Unbounded gaps and bounded gaps cannot both hold. Periodicity is crossed out. By the lemma, a number whose expansion never becomes periodic is irrational. So F contains no rational number. Second, F is perfect. Translation by A is an isometry of the line. It moves every point by the same amount, preserving all distances, hence preserving closed sets and limit points. E is perfect, so its translate F is perfect too, and F is certainly non-empty. A non-empty perfect set with no rational inside. By part 1 of this video series, it is even uncountable, an uncountable crowd of numbers, every single one irrational. And that closes part 2. We built the discrete world, audited 5 metrics, proved compactness with bare hands, broke the nested sets theorem twice, watched Heine Borel fail among the rationals, and crowned the set of 4s and 7s, finishing with a perfect set that dodges every rational number. In part 3, separated sets, connected metric spaces, convex sets, separable spaces, and countable bases. If this kind of careful, step-by-step analysis is useful to you, consider liking the video and subscribing. See you in part 3.